Hello everybody, and we start our last lecture in this year 2020. So section 27.1, lecture 27th, and let me call it like it is written in your lecture notes, different exercises with solutions. But I don't plan to give the same exercises which I given in your lecture notes. I think they will be given in your seminars. Instead of that, I plan to devote it to main tools to find limits with the help of asymptotic expansions. More often it is used the term Maclaurin expansions or Taylor expansions, but I tried to explain you there is an essential difference between them. So asymptotic expansions are more convenient from my point of view. So the first example is the same as in your lecture notes in section before that. We will find the limit square root of 1 plus 2 tan x minus e to the power x plus x squared over x squared arc sine x minus sine x. Okay, so we'll denote numerator as n of x, square root of 1 plus 2 tan x minus e to the power x plus x squared, and denominator by d of x, that is arc sine x minus sine x. The first step is to understand how long we should proceed in finding of asymptotic expansions. There are two possibilities to decide what to do. One of them is very simple, just start with some fixed power, let's say 3, and in fact most of examples which I used in written examinations and so on are suitable for this method. Just stop on power 3. But in some of examples you can decide it more precisely because of rather simple expressions when you see immediately or almost immediately which power is suitable. So for that reason, let us start with denominator, because it is easier to help us to decide where to stop. I'll write general expansion for sine x. For sine x we know the expansion is of that kind in general. Okay, I don't remember now what I used last time, and no, sorry, here and just either 2n minus 1 or 2n plus 1, I don't remember, it doesn't matter. Okay, so that is general expansion plus little o of x to the power 2n plus 2 as x tends to 0. Now we should find the expression for arc sine x. So how to do? If we denote f of x is arc sine x, then the derivative f prime of x is 1 over square root of 1 minus x squared, or 1 minus x squared power minus 1/2, and it means that we can use the expansion, one of main expansions, 1 plus t to the power alpha is equal to 1 plus alpha t plus alpha times alpha minus 1 over 2 factorial t squared plus so on, plus alpha, alpha minus 1, so on, alpha minus n plus 1, and factorial to the power n plus little o of t to the power n as t tends to 0. That is one of main expansions, which is suitable for us, because you see we can substitute t equals to minus x squared and alpha equals to minus 1/2. It gives the expansion of the following kind. So 1, let's substitute, so plus alpha is minus 1/2 times t, what is minus x squared, first term. Second term, alpha minus 1/2 times alpha minus 1 minus 1/2 minus 1 over 2 factorial times minus x squared power 2 plus so on, plus, okay, I will write in general, minus 1/2 minus 1, so on, up to minus 1/2 minus n plus 1 over n factorial times minus x squared power n plus little o of, we had t to the power n, so I should write x to the power 2n, but we also may observe that because of evenness of our function, the function is even, so we have only even degrees in our expansion, and it means that no term of x to the power 2n, so we may assert even more than it is written in our main expansion. So that expansion is valid as x tends to 0. What is it says in particular? Look, that is an expansion for f prime of x. The expansion, Maclaurin expansion. The expansion is Maclaurin expansion. So it means that coefficients are derivative at 0. So we have f prime at 0 is 1. F double prime at 0, that is f prime of prime at 0. So maybe it is better to write it here like g of x, do not mix. Then you see g of 0 is 1 by general Maclaurin expansion. G prime at 0 is 0, no first degree, we have no first power. Then for x squared, you know, the coefficient, general coefficient, let me recall, is g double prime at 0 over 2 factorial times x squared. That is second term with second degree, right? So look at the coefficient in x squared. It's 1/2. So it means that double prime at 0 is 1. Okay, so I think I can stop here. Why? Because, look, now look, come back. G is nothing else but f prime. So f double prime, f prime prime, so it's g prime at 0, it's 0. F third derivative at 0, what is f prime second derivative, or g second derivative at 0 is 1. That is what we computed. And what it gives to us, look, so we know what is the expansion of arc sine in general. Maclaurin expansion will be f of 0 is 0, then plus f prime at 0, 1 times x, plus 0, what is second derivative, times x squared, plus third derivative is 1 over 3 factorial x cubed, and plus O small of x cubed. Why I decided to stop here? Because of, look, if we look at the denominator, arc sine minus sine, what is g prime equals to 0, g prime at 0 equals to 0. Because what is g prime? G prime is f prime prime, second derivative. Sorry, g prime at 0. Why g prime at 0 is 0? The question, right? Look, we have Maclaurin expansion here. Let me recall general Maclaurin expansion. G of 0 plus g prime at 0 x plus g double prime at 0 over 2 factorial x squared plus so on. Oh, sorry, not so on, plus, let's say, O small of x squared if we decide to stop on second term, right? We decided to do it. Look, this is general Maclaurin expansion. Compare those two lines, and what you see? G of 0 is 1, g prime at 0 is 0 because no x here, and g second derivative is 1 because, yeah, we have 1/2, that is 1/2. Okay? Yeah. So let me go back to our denominator. So look at the difference between arc sine and sine. So arc sine is written here, x plus x cubed over 3 factorial. So, and now it's clear we were perfectly right in deciding to stop on cubic. Yeah. So minus, substitute x minus x cubed over 6 plus. So if we decide to stop on n equals to 3 for sine, then we should write like that. And you see now, we cancel x, and x cubed is not cancelled. So that is x cubed over 3 plus little o of x cubed as x tends to 0. And it shows that our decision to stop here was correct. Why? Because what we need smallest non-zero power of x, non-zero coefficient in power of x. Smallest non-zero coefficient in a power of, no, not correctly, not smallest coefficient. Non-zero coefficient in smallest degree, in smallest power of x. So we need to find smallest degree of x with non-zero coefficient. That is correct in spelling. Okay, so yeah. So you see, denominator shows us that we should stop on the third degree of axis. Now we know that for the numerator also we need to stop on the third degree. Okay, let's compute now. So many. Okay, so let's start with tan x. So tan x can be represented as sine x over cosine x. So we know that we should stop on power 3. So x minus sine x was used, x cubed over 6 plus little o of x cubed over 1 minus x squared over 2 plus little o of x cubed. And now how we can proceed here. Recall that a particular case of this expansion for alpha equals to -1 and t equals to -x will be very simple, which is, roughly speaking, you should cut geometric progression, the sum of geometric progression. 1 plus x squared plus so on plus x power n plus little o of xn as x tends to 0. That is a particular case of this expansion. And we can use it here. How? We replace division by multiplication. So it means we write times 1 minus x squared over 2 plus o of x cubed minus 1. So you see that, okay, maybe I should replace t by minus x, maybe by, let's say, minus y. Why? And now look, y tends to 0, so that is our y now, right? So we use 1 minus y power minus 1, and it gives x minus x cubed over 6 plus little o of x cubed times, substituted, 1 plus x squared over 2 plus little o of x cubed And you see that since we are interested in powers up to third power, so it means that we don't need any more y. So we can write here, okay, I can write the next one to be sure. Squared plus O of this power yeah, that's in general, so that is y. yeah. And you see that when we take powers, x squared is x power 4. This is also little o of x cubed, tends to 0 faster than x cubed. That is also little o of x cubed. So what remains, we can rewrite it as x minus x cubed over 6 plus little o of x cubed times 1 plus x squared over 2 plus little o of x cubed. And now multiply and collect only powers no more than cube, and it gives x, and for x cubed minus 1 over 6 plus 1 over 2 plus 3 over 6, so plus x cubed over 3 plus little o of x cubed, as x tends to 0. So we have obtained the expansion for tan x, Maclaurin expansion, up to power 3. Now let's continue with square root of 1 plus 2 tan x. That is 1 plus 2 times x plus x cubed over 3 plus little o of x cubed. Yeah. So square root is power 1/2. Now you see, we use this main expansion with t equals to 2x plus 2x squared over 3 plus little o of x cubed. That is our t. Alpha is 1/2 now. And substitute what we obtain. We obtain 1 plus 1/2 times this, 1/2 times t, yeah, and plus next term 1/2 times 1/2 minus 1 over 2 factorial times t squared 2x plus 2x squared over 3 plus little o of x cubed squared, plus we need one more term, plus 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial times 2x plus 2x squared over 3 plus little o of x cube plus, I should write also little o of this t, 2x plus 2x squared over 3 plus little o of x cube cube. So what I did, I just substituted into 1 plus t power alpha into this expansion. This expansion I used for n equals to 3, so we stopped on the third degree here, right? And I substituted t equals to this one, alpha equals to 1/2, so n equals to 3, right? N equals to 3. That is our main expansion. Now, what we obtain then? So maybe I will not continue this equality. Instead of that, come back to the expression for the numerator. So square root of 1 plus 2 tan x, right? What is written here? So let's collect now what remains. So 1 plus x, then next term is sorry, I made a misprint. X cube is here. Cube. Let me replace everywhere by cube. Cube. There is a misprint. Okay, cube. Okay. So, okay. Let's continue. So, next term which is necessary for us, this cube plus x cube over 3. Now, for the second term, we should take square of this expression, and we are interested only in powers no greater than cube. So if we take square of the first term is okay, but all other terms, including double product, are not necessary for us because they give larger powers of x, right? So what remains? Yeah, just we have 4x squared. Here we have minus 1 over 8. So minus 1/2 x cube, x squared, sorry, x squared. That is, so minus 1 over 8 times 4x squared. All other terms will be in little o of x cube. For the next term, also, when we take cube of this expression, only x cube remains here. So 8x cube. Here we have 1/2 times minus 1/2 times minus 3 over 2. It gives 3 over 8 times 8, just 3 over 6, 1/2 again, plus x cube over 2. All other powers will be in little o of x cube. Okay, that is this term. Then I substitute main expression for exponent, the first main expression, 1 plus x squared over 2 plus x cube over 6 plus little o of x cube, right? And then plus x squared. That is the numerator. So altogether, what remains then? Look, 1 is cancelled, x is cancelled, x squared over 2 is cancelled. So it means, as it should be, only cubes remain. So now I can substitute the results. So our limit is equal to the limit as x tends to 0. So what remains for the numerator? Look, 1 over 3 plus 1/2, it gives 5 over 6, minus 1 over 6, it gives 2 over 3. So 2/3 x cubed plus little o of x cubed over, for denominator, x cubed over 3 plus little o of x cubed. So we divide by x cubed and cancel thirds. It gives 2 plus little of 1 over 1 plus little of 1, that is 2. Okay. Now I think, who is Apeiros? Okay. So the result is 2. Is it? Yeah. Coincides with what is written in your lecture notes. Okay, now, yeah, you see that, of course, here I gave many details. And by the way, this idea to use derivative to find Maclaurin expansions can be written in general, so maybe that is a little bit more theoretical example. So let me write it as a lemma. We could use it here instead of writing down this in a particular case. Lemma. If f prime of x equals to a0 plus a1 x plus a n x power n plus little o of xn as x tends to 0 is the Maclaurin expansion, then the Maclaurin expansion for f of x is f of x equals to f of 0 plus a0 x plus a1 over 2x squared plus so on plus a n over n plus 1 x power n plus 1 plus little o of x n plus 1 as x tends to 0. So we can proceed in general like that. So the proof is like we did before, so it means denote g of x by f prime of x. Then we know that kth derivative at 0 is just ak times k factorial because of the expression for coefficients and uniqueness for Maclaurin expansions, for asymptotic expansions, sorry. So then we have fk at 0 is equal to f prime k minus 1 at 0. That is g k minus 1 at 0. So we have a k minus 1 times k minus 1 factorial, and then it gives the coefficients, right? So f of x equals to f at 0 plus f prime at 0 1 factorial x plus second derivative at 0 2 factorial x squared plus so on plus n derivative for the n plus 1 at 0 n plus 1 factorial x power n plus 1 plus little o of x power n plus 1 as x tends to 0, and then we substitute, and it gives, after cancelling factorials, it gives precisely the formula. So this lemma in fact was used to find the expression for arc sine x once we know the expression for its derivative. Here, right? Okay. Now next example. Example 2. Example 2. So I took this example from problem book, which is used here for Russian students. 2x over x minus 2 plus logarithm of e plus x e to the power x plus 1 power 1 over x cubed. Okay. First of all, we have the limit of the form u of x power v of x. Let us look at this limit. If we substitute 0, then we have, look here, 0, logarithm e is 1, so is 1. Limit as x tends to, let's say, 0 plus minus of v of x equals to 1 over x cubed tends to correspondingly plus or minus infinity. Okay, let's have a break then. Okay, let's continue. So it means, looking at those limits, it means that we have indeterminacy of the sort of the kind 1 power infinity, and we know how to compute such limits. It was at the very end of chapter 4, the last section of chapter 4, and that is exponent. There was an assertion, exponent of the limit of v of x times u of x minus 1. That is a possibility to compute limits of this kind when we have this relation for the base and the exponent. Okay, so let me compute the limit x tends to 0, v of x times u of x minus 1. What is it? Just substitute limit x tends to 0, v of x is 1 over x cubed, so x cubed, u of x minus 1, so we should substitute logarithm e plus x e to the power x plus 1 minus 1. Okay, so here the denominator shows immediately we should stop on power 3, only up to 3rd degree, no more. So let me collect everything in one equality now. Here we can represent as minus x times 1 over 1 minus x over 2. So we divide by 2x, numerator and denominator. We obtain then x over 2 minus 1, and I'll put sorry, I said divide by 2x, sorry. We should divide by 2, both numerator and denominator. Divide by 2, and then put minus outside of the ratio. Okay. And here we represent by product, so logarithm e and logarithm of product equals to the sum of logarithms. Logarithm 1 plus x e to the power x. So we took one term, one multiplier e outside of the bracket, and also don't forget to write minus 1 over x cubed. Now once again okay, this was a particular case, 1 over 1 minus y today, so I'll use it, and minus x times, so 1 plus x over 2, y equals to x over 2. We use one of main expansions for 1 over 1 minus y. And we can stop here just on the 2nd degree. Why? Because after that, we don't forget, we will multiply by x, and it gives x cubed. So little o of x squared. We can stop for this ratio, we can stop in x squared. Then logarithm e is 1, so we cancel those terms. And okay, I can write firstly x e to the power x. So here we'll stop again on x squared because of product by x, little o of x squared. Yeah. Then equals to the limit as x tends to 0. So multiply by x, it gives minus x squared over 2 minus x cubed over 4 plus little o of x cubed, plus, now we use the last main expansion in Maclaurin formulas for logarithm, and there is our variable which we substitute. So I'll start with this variable, which is x plus x squared plus x cubed over 2 plus little o of x cubed. Maybe I should have it somewhere for convenience. That is y minus y squared over 2 plus y cubed over 3 plus little o of y, as y tends to 0. So y is this expression. Here I wrote just y. The next is minus y squared over 2 minus x plus x squared plus x cubed over 2 plus little o of x cubed squared over 2. Then plus x squared plus x cubed over 2 plus little o of x cubed over 3 plus little o of this huge expression. Cube. Right? That is the numerator, the long expression for the numerator. And denominator is x cubed. Okay, equals to the limit as x tends to 0. Now let's compute. We cancel x. Okay, so minus x squared, minus x squared over 2 plus x squared gives x squared over 2 with plus x squared over 2. Also, what is about cube? Cube minus x cubed over 4 plus x cubed over 2 gives plus x cubed over 4. Okay, now let's collect what remains. Minus x squared over 2 from squaring. Also from this term, that is very popular mistake of students. Look, when we take square of this expression, so what is square of a sum? It contains squares of each term plus double products of different terms. What's about double products? Look at this double product. X times x squared gives x cubed, and we are interested in cubes. So double product gives 2x cubed divided by 2, so minus x cubed. But all other terms here in square. So square of x squared is x power 4, degree is greater than 3. all other double products also have larger powers. So the only, not the only, so we have just two terms from this, minus x squared over 2 and minus x cubed. And then for this cube, only cube of the first remains, because all other terms will contain larger degrees of x. So plus x cubed over 3, and all other terms contain larger power of x, so little o of x cubed over x cubed. Now you see x squared disappear, and what is for cubes? So common denominator is, least common denominator is 12. So 3 minus 12 minus 9 plus 4 minus 5. And it gives limit as x tends to 0 minus 5 over 12 x cubed plus little o of x cubed over x cubed, and we divide by cube. Okay, I will write maybe last time in details what remains, and that is minus 5 over 12. So the answer is, take exponent e to the power minus 5 over 12. That is the end of the solution. No questions. Okay. And the last example for that section. So example 3. Limit as x tends to 0 plus sine hyperbolic x minus logarithm x plus square root of 1 plus x squared power 1 over logarithm x. Here, once again, we have the limit of the form x tends to 0 plus u of x power v of x, but if we compute the limit of u of x, that is, look, 0, sine hyperbolic of 0 is 0, logarithm 1 is 0, so it's 0. And also limit of v of x. Logarithm tends to minus infinity, 1 over minus infinity is 0. So we have indeterminacy of a different form, 0 power 0. And it means we cannot use this rule. So this rule cannot be applied here. It should be wrong. could try to use this rule. But how we can proceed? We can take exponents in any case. So that gives exponent of the limit as x tends to 0 plus of v of x times logarithm u of x. That is valid in any case. Doesn't matter which kind of indeterminacy, in fact, we have. So it's valid also in the cases when no indeterminacy at all, just substitution. Okay, so let's compute this limit separately. X tends to 0 plus v of x times logarithm u of x. V of x is 1 over logarithm x, so I can rewrite as ratio logarithm x, and in the numerator logarithm sine hyperbolic x minus logarithm x plus square root of 1 plus x squared. That's it. Okay, let me erase. Okay, so we should decide once again where to stop. Now it is not clear from the point of view of general considerations, I mean, because it's very difficult to understand. So there is another rule which I mentioned before: just stop on the third degree, because in most cases it's okay, and it's okay in our case. And of course you may ask me what to do if it will be not okay. Then the answer is you should stop later. You should find expansions up to larger powers. Then that is. But unfortunately, you can decide it only after considering the expansion. So let us stop on the third degree. Okay, then let's write firstly square root of 1 plus x squared. That is 1 plus x squared power 1/2, 1 plus 1/2 times x squared, and then we observe that next term will be with x power 4, and we are not interested in everything with larger power than cube. So we have Maclaurin expansion like that. Then logarithm of x plus square root of 1 plus x squared. If we substitute, then we have 1 plus x plus 1/2 x squared plus little o of x cubed. And, oops, let me, it was written here and I erased it. It was a mistake, of course. Logarithm 1 plus y minus y squared over 2 plus y cubed over 3 plus little of y as y tends to 0. So that is y now. And if we substitute, what we obtain? This y is x plus 1/2 x squared plus little o of x cubed. Then minus 1/2 x plus 1/2 x squared plus little o of x cubed squared plus 1/3 cube of this expression plus little o of this cube. And now let's compute what is it. So we have x plus x squared over 2, then taking square here. Square of the first gives minus x squared over 2. Then double product. Also we need to take into account the double product. What is double product here? Just x cubed. So minus x cubed over 2. All other terms in this square contain larger powers of x than cube. X power 4 and also those powers also. Cube. In cube only one term we need. Just the cube of the first, x cubed plus x cubed over 3. All other terms are in little o of x cubed. And that is, what is it? So cancel x squared, x minus 3 plus 2 minus x cubed over 6 plus little o of x cubed. X tends to 0. That is for the logarithm. Now, sine hyperbolic. Sine hyperbolic is e to the power x minus e to the power minus x over 2. If we substitute 1 plus x plus x squared over 2 plus x cubed over 6 plus little o of x cubed minus, now substitute instead of x here minus x. It gives 1 minus x plus x squared over 2 minus x cubed over 6 plus little o of x cubed over 2. And so we cancel 1, we cancel x squared over 2, we double x, so what remains after dividing by 2? X plus x cubed over 6 plus, okay, I should write little o of x cubed, but we can observe that also, okay, let me stop here, just cube with cube. In fact, we can write here x power 4, but it doesn't matter. And you see that I didn't write it in among main expansions, but you see how to obtain sine hyperbolic from exponent. Just choose odd powers of x. That is a rule, right? Cosine hyperbolic, you should choose even powers of x from the expansion for the exponent of x. Okay, now we can substitute. So what we have, the limit as x tends to 0 plus logarithm of substitute expansions x plus x cubed over 6 plus little o of x cubed minus, for the logarithm we have x minus x cubed over 6 plus little o of x cubed, and logarithm x is here. And you see, fortunately, we cancel x, but we don't cancel x cubed, because why fortunately? Because if cubes would cancel also, what it means, canceling of x cubes? It means that we made a wrong decision from the beginning to stop everywhere on cubes, and in that case we should reconsider everything from the very beginning to stop on the next power of x. But here it's no problem, so what remains? We have logarithm x cubed over 3 plus little o of x cubed over logarithm x. Now, what to do with this expression? So let's use properties of logarithm. So just take as a, okay, I write in details, logarithm x cubed times everything else, so, and then logarithm of the product is the sum of logarithms, so logarithm of 1/3 plus little o of 1. Oh, sorry, I forget limit. Limit as x tends to 0 plus logarithm x. Now, okay, I put 3 here again by properties of the logarithm. And then look what we have. Both numerator and denominator tend to minus infinity as x tends to 0 plus. So we can divide both numerator and denominator by logarithm x. And what it gives? It gives limit as x tends to 0 plus 3 plus logarithm 1/3 plus little o of 1 over logarithm x. And now look, numerator tends to logarithm 1/3, that is a finite non-negative number, non-zero number, in fact it's negative, non-zero number, and denominator tends to infinity, minus infinity, so the expression tends to 0, and it means the limit equals to 3. So we can find finally the answer to our example, e to the power 3. That's it. Okay, no questions. Very good. These are main examples of computation of limits and in fact like a summit for the theory of limits, in fact. And that's all for this section then. And in fact, we can start then. It's not a good idea to start a new. Okay, let me consider one more exercise that I didn't take. Then I didn't take with me other exercises from that section. Okay, maybe it is not a good idea to start new chapter at the very end of 2020, but let it be. So we start new chapter. Chapter 6, which is called the study of functions by methods of differential calculus. And very short section 27.2 then, and let it be just one theorem. Conditions, how it is called, for a function to be monotonic. For a function to be monotonic. And here there is a difficulty which is in different terms. Let me recall that if we have this implication, then this is f is strictly increasing. That is what was used before. And if we cannot guarantee strict inequality but non-strict only, then f is increasing. That was the definition from former analogous for decreasing functions. And you see in your lecture notes now different understanding is used. So now this is increasing and that is non-decreasing. I'm sorry for this mixture. It's yeah. You see that the word increasing is used in different senses in two parts of lecture notes. I'm sorry. Okay. So proposition. proposition. So, okay, suppose f of x is differentiable on an interval a b. Doesn't matter what is. Okay, so the first one, f prime of x is non-negative for all x in AB, then we deduce that f is increasing in this sense, and if f is increasing, then for sure differentiable function derivative is non-zero for all x in AB. Second, if first derivative is positive for all x in the interval, then for sure f is strictly increasing, and then f prime of x non-negative only for all x. So we cannot assert here strict inequality, unfortunately. And okay, analogous conditions for decreasing functions. F is decreasing. I use the old sense, right? F prime of x is non-negative for all x, and analogous, the last is f prime of x negative for all x, hence f is strictly decreasing, hence derivative is non-positive. We cannot assert that the derivative is negative for strictly decreasing functions. So proofs are very similar for all those. So let's do the very first. So take x1 less than x2, both of course in AB, so AB. Then we use Lagrange mean value theorem. There exists a point C in x1, x2 in the interval. There exists C in the interval x1, x2 such that we have this inequality. And if the derivative is non-negative, then what we deduced, that is positive, right? Derivative non-negative, hence this is non-negative. And it means that f is increasing. So the first implication is proved. Now if f is increasing, then look, f prime, let's say plus at a point x 0. That is the limit as x tends to x naught plus f of x minus f of x naught over x minus x naught. Now look what we have here. Denominator non-negative because x tends to strictly positive. Numerator is non-negative because of f is increasing. Hence, the limit is non-negative. Analogously, we can check the limit from the left-hand side. And it gives the second implication, and all other implications are proved in a similar manner. Okay, that's all for today then. And Happy New Year, and also Merry Christmas for Eastern Christians. Okay, that's all.